Hi everybody. I'm from Icon National Lab, and today it's my pleasure to present to you my work on resilient solution for tomographic reconstruction application with Spatial. So let's start a little bit with a little bit background about tomographic reconstructions. So this is kind of application where we want to reconstruct the 2D or 3D uh, structures of some unknown objects using the X-ray beams. So the setup of the application is very simple. So we have in the scientific instrument like the APS at Argon, we have the X-ray beam, and then we penetrate the X-ray beam to the object that we want to discover the internal structures. And we rotate the object at multiple angles, and we collect the projections of the beams, go through the projects and send the projection into the high performance computing infrastructures like the Aurora supercomputers. And inside the computer, we deployed uh, tomographic reconstruction workflow in order to reconstruct the, sorry?
You're fine.
Okay. Yeah, the 2D or 3D image of the object based on the projections. So the workflow will consist of two parts, two key parts: the data acquisitions, where we will collect the projection from the instruments, and then this component will distribute the projection into multiple reconstruction tabs, and these tabs will work together to provide the final reconstruction images. And one problem with the workflow that is very highly computation intensive. So for example, for each computation that handled by the reconstruction task, is basically the process basically is an iterative computation where we try to match the 3D or 2D reconstruction with the measurement we collect from the projections in order to reconstruct high quality images, and this requires a lot of computation if we want to have very high quality of reconstruction. And in order to handle the high volume, in order to get the larger views or the figures, we also need a lot of computation tasks to handle multiple projection, and this requires a lot of computation with multiple processes. And when we run the workflow under the failures environments, it can be very catastrophic. So here in the figure on the right, on the left, we have that the x-axis showing a number of reconstruction tabs we need in order to reconstruct the image. And you can see on the blue line the failure frequency that the application, the whole application had to tolerance if we have the average mean time to failure of 1 day per each process. And we assume that each process will last just for half of a day. And you can see that the effect on the runtime of the application with the red line in the graph is that it has an exponential growth in the runtime, because every time a task of the application receives the failures, the whole application has to restart because of the highly coupled between the reconstruction tab. And therefore, the execution time just go very high when we add more tab into the workflow, and easily becomes infeasible at large scale deployment. So how can we solve the problem? So we have 3 steps and 3 solutions for that. First, we have to decouple the reconstruction task in a way that we will leverage the parcel workflows API. So basically, we will try to isolate each reconstruction task into a single parcel worker, and by that, we can prevent the failure from propagate to the other task in the workflow. So the failure only affects a single task or the workflow. And secondly, by using the parcel, we can leverage the parcel resource management framework in order to scale the application easily without needing any further effort from the application side. And second, in order to enhance the resiliency of the application, we also have the periodic checkpoint where we have the parcel worker to periodically save or captures the local state of each of the reconstruction task into parallel file systems, so that every time the failure happens, we can rely on the parcel retry mechanisms to cleanly release the failure parcel worker and spams the new parcel worker to execute the new reconstruction tab using the checkpoint to restore the computation. And we also implementing a smart load balancing inside the data acquisitions, so that every time the new workers restart, they can rebalance the load amongst the surviving tasks and the new tasks, so that the new task will not be take a lot of loads and will not slow down the overall execution times of the whole workflow. And here are a few results we have with the solution. So we run the solution with 2D reconstruction forms around 180 2D frames, and we run for 64 reconstruction tasks using the Power supercomputers. And we also simulate the failures using the memoryless randoms. And the results show in the figure on the right, where we have the axis represent the mean time to failure for a single task. And you can see that without the resiliency introduced by Parcel and introduced by our low balancing mechanisms, you can see that the runtime to run just skyrocketing increasing when we increasing more failure. And as when we have around like 1,000 failure a day, it become infeasible where the workflow take around more than 3 days to complete. But with failure, we can significantly reduce the impact of failure, where, for example, with around like 100 failure a day, we can reduce the execution time by half compared to no resiliency at all. And with our smart load balancing, where we try to rebalance the load between the new task and the surviving task, we can further reduce the reconstruction time and make it feasible under very high failure frequency. So given that encouraging result, the next step that we want to apply the solution for real-time reconstructions, where we will try to not only address the resilience problem in the case of the process failure, but we also want to address the problem of communication failure as well, in order to enhance the quality of service of the reconstructions, and also want to run it on a larger scale, not just 64 processes, but maybe more than that, maybe 1,000 or even more. So I think that's it. Thank you.